Hello everyone. Today we will see principles of deadlock under the topic concurrency control in operating system. Now when we see the operating system, there are various processes working under this as a total operating system, and this system consists of various resources. The resources could be given the names like R1 to Rm, and suppose the resources are CPU cycles, memory space and IO devices. Now these resources could have multiple instances as well, like multiple IO devices are there of same type, multiple USB ports are there, then multiple memory space is available. So we say Ri resource is having Wi number of instances. Now when we want to utilize a particular resource, the process will request for a particular resource, then it use the resource and release the resource. So this is general behavior of any process under the operating system. Now, when we say these resources are used by a particular processes under the operating system, there is an important condition which occurs during this resource utilization, which is called as deadlock. So this deadlock is a permanent blocking of a set of processes that either compete for system resources or communicate with each other. So in this case, the processes are blocked by other process which is holding a resource required by the first process. And there is no efficient solution to handle this deadlock situation. In this case, the various resources required by the process are conflicting, which causes this deadlock to occur. And this deadlock causes various problems. To understand this deadlock as a concept, we have four principles under this deadlock. So let us see these principles in the next slides. So the first principle is reusable resources, the second is consumable resources, third is resource allocation graphs, and the fourth is conditions for deadlock. We will see these resources in the next slides. The first is reusable resources. Now various resources are there in the operating system which are reusable. It means that the same resource can be used by multiple processes at different times, and resources does not get exhausted. So the process obtain the resources that they later release for the reuse by the other processes. The reusable resources could be processors, IO channels, main and secondary memory devices and data structures, then like files, databases, semaphores and etc. So various software as well as hardware resources could be reusable resources. Now this deadlock occurs if such a process holds one resource and requests for the other. In this case, the reusable resources are available for the usage by various processes and they are waiting for other resource which is held by other process. So in this scenario, if you see, there are two processes P and Q and the actions given by this process in this particular block. So the process P requests for resource D and log the resource D. At the same time, process Q requests for the resource T and log the resource T. Now, after that, the process P requests for the resource T and log the resource T. Now, when it is requesting the resource T, actually the resource T is already locked, so it cannot get this resource T at this particular instance, and it is waiting for the resource T. At the same time, the process Q requests for the resource D. If you see as a Q2 instruction here, in that case, it also waits for the process P to finish. So at this particular stage, we see the both processes P and Q are waiting for each other to release the resource which is held by other process, and the deadlock will occur. So this is the first principle for the deadlock, which is the reusable resources. Now second is consumable resources. Now here the consumable resources means that is a resource which is produced and then get destroyed. In this particular consumable resources, we have the interrupt, signals, messages, information in the IO buffers and various types of instructions. Now, if in this particular consumable resource is there which is a blocking, like the example is given, if the receive message is blocking, the deadlock may occur. In this case, the sender is sending the message and the receiver is waiting for the message from the sender, and again the sender wait for the receiver to send the message or the acknowledgement we can say, and the receiver is blocking, so receiver cannot continue until it get the resource as a message from the sender. So here there are various and rare combinations of events that causes the deadlock under this consumable resource principle. So if you see this particular example, there are two processes P1 and P2 and P1 is having the receive P2 and P2 is having receive P1 and both are blocking receive. So in this case the P1 is waiting for the receive from P2 and P2 is waiting for the receive from P1 and both are blocked. So this is an example of deadlock with the consumable resource. Now the third principle of deadlock is resource allocation graphs. Now as we have the concept of graph, we have this resource allocation graph as a directed graph with the process and the resources. Now the processes request for the particular resources and the resources are held by particular processes. And as we already said that we have various instances of resources, we can show a particular dot for that particular instance of a resource. So in this particular graphs, we have two types of edges, request edge and held by edge. So let us see more about this resource allocation graph in the next slides. Here we have the resource allocation graph, which is a normal graph with a set of vertices and set of edges. So V is a set of vertices and E is a set of edges over here. Now this V could be having two types of vertices, the process as a vertices and the resources as a vertices. Here we have a request edge, which is a directed edge from P to the R, which is example Pi to Rj, and the assignment edge, which is a directed edge Rj to Pi. Now there are various notations to see under this resource allocation graph. So if you see, process is shown by the circle as we have in this particular slide, and the resources, suppose it is having 4 instances, then 4 small dots are shown under this particular resource as a square. Then we have the process Pi requesting an instance of Rj, then Pi to Rj we have a edge as it is shown in this third point, and if a Pi is holding a particular instance of Rj, then there is a edge from a circle inside this Rj to Pi. So we have the request edge and the hold by edge in this graph. Let us see the example of this resource allocation graph. We have a sample graph with the 3 number of processes and 4 number of resources, and the set of edges are also given for this particular resource allocation graph, and we have 1 instance for R1, 2 instances for R2, 1 instance for R3 and 3 instances for R4. We can draw this graph as we have on this slide. We have the edges from P1 to R1, R1 to P2, P2 to R3, R3 to P3, and we have the edge from R2 to P2 as well. Now in this particular graph, we have the edges as shown in the previous information. Now suppose we add one more edge from P3 to R2. Now in this case, this graph will have a cycle. The cycle is R2 to P1, P1 to R1, R1 to P2, P2 to R3, R3 to P3 and P3 to R2. This is outer cycle, and there is another cycle which is, we can say, R2 to P2, P2 to R3, R3 to P3 and P3 to R2. So as this particular graph is having cycle, the cycle is the necessary and sufficient condition for the existence of deadlock. So we can say this particular resource allocation graph is showing the deadlock of resources by the processes. Now if we see this particular different resource allocation graph, we have 2 resources, the 2 instances of each and 4 number of processes, and we have a cycle in this graph as well. P1 to R1, R1 to P3, P3 to R2 and R2 to P1. Now here again we have the cycle. So if a particular resource allocation graph is having no cycle, then there is no deadlock, but if a particular resource allocation graph is having cycle, then there is may or may not be having the deadlock. So if you see this particular example in the next slide, we have P1 to RA, RA to P2, P2 to RB and RB to P1. So we have the circular waiting over here and there is a deadlock. But if you see the second graph, P1 to RA, RA to P2, P2 to RB and RB to P1. Now in this case, we have multiple instances for the resources RA as well as RB. So there is no deadlock whether there is a cycle. But in the first graph, we have cycle and we have the deadlock as there is single instance of the resource. So number of instances of resource is very important to understand whether there is a deadlock or not. So what we say, If the graph is not having cycle, then there is no deadlock. But if the graph is having the cycle and if there is only one instance per resource type, then there is surely a deadlock. But if there are several instances per resource type, then there is a possibility of deadlock, as we have to consider number of requests and number of instances for a particular deadlock. So considering all these principles, we have 4 necessary conditions for deadlock to occur. So these are very important conditions to consider for the deadlock occurrence. So first is mutual exclusion. It means that only one process may use a resource at a time. So if we consider a single instance as a one resource, then one process should use a resource at a time. So it is a mutual exclusion. Exclusively usage is given to the process. Now the second condition for deadlock is hold and wait, which is when a process held a particular resource, it should wait. A process may hold allocated resources while awaiting assignment of others. So holding a resource and waiting for other, that is also allowed in this situation. Now the third important condition for the deadlock is no preemption. Here no resources can be forcibly removed from a process holding it. So unless and until the process finishes with the usage of the particular resource, it should not release it. So no preemption. In between it cannot release a resource unless the complete usage is done. And the 4 important condition for deadlock to occur is circular wait. In this case, a closed chain of process exists such that each process holds at least one resource needed by the other next process in the chain. So this is very important, which is a like graph cycle that which we have seen the resource allocation graph. Here one process is waiting for the other process which is holding the resource required by the previous process. So there is a circular wait. The cycle is completing. So if all these 4 conditions are held, there is a guarantee that the deadlock will occur. So mutual exclusion, hold and wait, no preemption, and circular wait. So we have seen all these 4 principles in this video, in these slides. Thank you.